Hi everyone, we're starting a new chapter. This is chapter 10 and we're moving away from proportions and we're starting to talk about means today. So this whole chapter is really about how we estimate means. So the inference procedure that we're going to kind of start with today and understand how it works is a one sample Z interval for the population mean. Okay. So this would be how we do a Z-interval, right? When we have proportions, great. And this will be what we do when we have means here. So with means, we need to know the population standard deviation. Okay, the same conditions apply. But the problem is you have to know the population standard deviation. Let's be real, how often is that going to happen? If we know the population standard deviation, why are we doing a statistic? So this one is a little bit tricky and we're not going to use this very often. And I want to prove to you why this is difficult. So what I want you to do is I put a link in your Teams page and I want you to go ahead and go to this link now and I'll give you a little bit of time. So it's going to be this one here and again it's in Teams, so take a second, navigate to Teams, get your devices up if they aren't already. We're going to play a bingo game. Okay, so you're going to click on this thing called Simulating Confidence Interval. And I'm actually going to demo it for you right now, but you should have your statistics should be mean, your distribution should be normal, your method should be Z with sigma, as in the population standard deviation. I want you to change the population mean to 100, population standard deviation is 20, sample size is 4, and number of intervals is 1 with a 95% confidence. So I'll give you a sec to go ahead and do that. So here's what my screen looks like. And I have all the things set to what I just mentioned: mean, normal, Z with sigma, 100, 20, 4, 1, and 95. And I'm just going to hit sample, sample, sample. And you'll notice it's green here, which means that my interval captured the true population mean. So I'm just going to hit sample until I find one that did not actually capture the mean. So I just found one and I clicked past it. Okay, there's another one. So does everyone see that when I find one that doesn't capture the mean, it's red? Okay, so whenever you find a red one, I want you to yell bingo. And we're going to see how many times we do that until you get a running total of about 100. So why don't you go ahead and pause the video and everyone go ahead and do this. And we're going to go until you do about 100 samples and we're going to hear in the room how many times people say bingo. And yes, you do have to do this. Okay, so now we're back. Hopefully you didn't hear that many bingos, probably about 5%, not that often. But again, how often are we going to know what the population standard deviation is? Not that often. So we're going to do what we did before, where last time when we were doing proportions, when we didn't know P, we estimated with P hat. So our best estimate of the population standard deviation would be S of X, or sample standard deviation. So we're going to sub that in. So what I want you to do is change the method to Z with S. So you can see that right here. It's this lovely thing here. I want you to change it to Z with S. Everything else is going to stay the same. And we're going to play bingo again another 100 times. This time I want you to do the same thing, right? Click, click, click sample until you have about 100 runs, and I want you to listen and see how often people are in the room are saying bingo. So I'll go ahead and pause the video and let you go ahead and do that. Lots more bingos this time, right? Yeah, I mean, you're saying bingo all the time. And if you look at your percent, like it's nowhere near 95. Maybe if you're lucky, it's like 85 or something like that. So clearly that was not a good estimate. That did not capture the confidence level that we want. So we're going to try this new thing, and I want you to go to method this time, and you're going to change the method to using a t interval. Yep, we went from a z to a t. So I want you to try T, and we're going to play the bingo game again, another 100 samples, and I want you to hear how many times people say bingo this time. Okay, go ahead and pause the video. And we're back. Okay, so yeah, way less bingos. If you look, this was way closer to a 95% confidence level. So clearly, Z intervals aren't cutting it. They aren't going to work if we're going to sub in S of X, which is what we have to do because we don't know the population standard deviation. So scratch that first inference method I talked about. We're not going to do a Z. We're going to do a T. So the inference method that we're going to learn about is a one sample t interval for population mean. Again, the t is a whole new statistic. So let's talk a little bit about where that statistic comes from and what it's about. So here's kind of a picture of t distributions and kind of how they work. So we have this here. And this is just essentially the z distribution, right? If we have the population standard deviation, we calculate our z-score, everything's normal, everything's beautiful. Look at that curve. This is what we have done before. Okay, but t-distributions are different. So here's the distribution for what it would look like with this normal kind of curve, right? With our z distribution here. But this is what a T looks like. So I'm going to have you go ahead and pause the video and talk to your neighbor friend. What makes the T distribution different from the Z? Okay, and then coming back, maybe you said, hey, look, you've got way more outliers. Right? You've got way more in this region and in this region than the Z distribution. And it's actually shorter as well. So those are the differences that you're going to see with the T. And where does this T come from? Normally I don't talk about like history of statistics, but this one is hilarious. So the T distribution and the T inference procedures were invented by William S. Gossett. And he was born in 1876, died in 1937, and he worked for Guinness, like the Guinness Brewery, and his goal in life was to make better beer. And he used this procedure, like he was finding that he was trying to find the best varieties of barley and hops, and he was seeing that when you had a small sample size, he wasn't getting the confidence that he was before, so he invented this whole distribution, and his statistical work helped him become head brewer actually at Guinness, and he published under a pen name of Student. Because Guinness didn't want to know everyone's secret for how they were like selecting these things, and so it was often called Student T, the student's T distribution in his honor. So anyway, that's where the T distribution came from. It really came about finding better barley and hops for beer, which is interesting. So what do we use it for? We use it for when we need to estimate our S of X. Now what's different about a T distribution is there's a different T distribution for each and every sample size. That's right, a different slight curve for each sample size. So we specify a particular T distribution by giving its degree of freedom. And you're probably wondering, degree of freedom? I'm sorry, what? What? So the degree of freedom is essentially the number of values that are free to vary in a data set. The way we find it is the appropriate degrees of freedom are found by subtracting 1 from the sample size. So degrees of freedom equals n minus 1, we write the t distribution as t sub n minus 1. But you're probably still like, degrees of freedom, what are you talking about? Where is this coming from? So I think the best way when I say that a degree of freedom is the number of values that are free to vary in a data set, I think the best way to think about this was sort of define what free to vary means. So if I say, I want you to pick a set of numbers that have a mean average of 10. Okay, so think about that. 3 numbers that have a mean average of 10. Why don't you think some in your head for a second? Okay, so maybe you say 9, 10, 11, or 8, 10, 12, or 5, 10, 15. But once you've chosen the first 2 numbers in the set, the third is actually fixed. The third is like predetermined. You can't choose the third set. So there's really only 2 variables that are free, 2 numbers that are free to actually vary. And that's where the name comes from. Okay, so here's our t-distribution statistic, or our t-score. So instead of a z-score, now we have a t-score. So it's the x bar minus mu divided by our s of x divided by the square root of n, again, because it's a sample, so we always have to divide it by root n. So that is our lovely new t-score. That's right. Now we have z-scores. We've done with z-scores. Now we're using t-scores. I told you that each t-distribution was slightly different, so I want to actually show you a picture of what this looks like. Purple is our standard normal. Remember our standard normal, that is code for z-score, or our z distribution, right? So we have t when you have 2 degrees of freedom. That's meaning I don't have a whole lot of variables. You notice that it's actually shorter over here, like it's shorter here, and we're going more into the tails. Okay, and then with 9 degrees of freedom, a little bit more variables, it's a little bit taller, still a little bit more in the extremes than the normal. Okay, and as we approach normal, it gets closer and closer to normal. So this is going to be important for you to think about conceptually, is there's going to be a lot of questions on the AP exam that are like, well, what would a t distribution with 3 degrees of freedom look like compared to a t distribution with 25 degrees of freedom? So you want to be able to know that the smaller the degrees of freedom, the shorter the top of our curve, as in like less numbers at the mean, and you have more numbers in the extremes. So that's essentially what you need to know for the difference between what this looks like distribution-wise. Now let's be honest about tables for a second. Because it's a new distribution, we need to be able to read a new table. Now, honestly, do I use the Z table? Honestly, not really. I really don't. But I do use the T table. It's the one that I actually don't always bother to look up on my calculator. I find this one a little bit easier to use. So you can disagree with me and love your calculator and use it just fine. But I want to show you how to actually read it from the table first. So degrees of freedom appear in the row at the left here, degrees of freedom, and the confidence level is at the bottom. So to find your degrees of freedom, remember it's n minus 1 on the left, then move over to the appropriate C level on the bottom. So if I wanted a 95% confidence interval with 11 degrees of freedom, I would be like, okay, 95%, 11 degrees of freedom. Oh, that would be my critical value, 2.201. And that's how we do it. So that would be our critical value, which of course we call our T star, right, with the little asterisks. So instead of the Z with the asterisks, now it's T with the asterisks. Okay, so I'm in your OneNote just to show you what this looks like. So I'm under the content library, I'm under tables and formulas, and then I'm under tables. So this has been the table that we always look at, table A. We have our z-score, it's nice and comforting. We're going away from that. We're going to table B, D or T distribution critical values. So again, you can see here's my degree of freedom, and it even shows you like, hey, here's the critical value. So it has the degree of freedom, and then if you scroll all the way down to the bottom, you have your confidence level, tiny here. So if we go up to a 95% confidence level, we can look at the degrees of freedom. Now I want you to notice this. We go from 1 degree of freedom all the way to 30, and then something happens. It skips to 40, then it skips to 50, then it skips to 60. So what in the world do you do if you have a 65 degrees of freedom? If you're using a table, you use the smaller value. So you would round to 60. So if it's between two values, you always use the lowest value. Okay, so that's what you're going to do with this. And then you see this little infinity here. This infinity just means it's infinite, as in like tons of different degrees of freedom. That's actually your z-score. So check it out. Remember how your critical value for a z-score, when you were looking at like a z-score and you were looking at 95% confidence interval and you wanted to know what the critical value was, and I said, oh, it's 1.96. Look, it's right there. Isn't that nice? That's a fun little trick. So the infinity marker here is just your actual, like what the critical value for your Z would be. So all the rest of these, again, degrees of freedom, we look up your degrees of freedom, look up your confidence level, find it, boom, that's your critical value. If I'm at 42, I would go to 40. I'm at 49, I also go to 40. So you always go to the smaller value. So let's take a sec and let's get out your calculators, either your 89 or your 84. And I'm going to start with the 89s. If you don't have one with you today, you can look on with someone next to you. And just take a second, get out your calculators. Some people find the calculator easier. I don't necessarily, but I'll talk you through how to do it. So if you go to Stats List Editor, which is where we live in the TI-89, you're going to go to F5 Distributions, and you're going to find the inverse, right? Because we want our critical value. And you're going to look for the T inverse. Now what's tricky about this is you have to enter the area to the left. So let's say I want a 95% confidence interval. Well, that's in the middle. So I have to think to myself, well, 95 confidence, 100 minus 95 is 5. 5 divided by 2 is 2.5. So 100 minus 2.5 is 0.975. So that's the area I have to enter if I want a 95% confidence level, right? So it's a little trickier that way. Then I'll have to input my degrees of freedom, and then I hit enter. So on the 89, I just thought I'd show you this one because I'm not as familiar with it and I can never remember distribution here. So we're going to go to second vars, which is where we have our distributions on this calculator. And then we're just going to arrow down into inverse T. And then I would put, again, that same area, 0.975 will give me the confidence interval for a 95%. And then I'm going to go down to 11 degrees of freedom, paste, and then I get my critical value. So it wouldn't be a new inference method if we didn't talk about conditions for estimating. So that's what we're going to talk about now. Again, some of these conditions you might not need to write down because you know them so well. So we're going to start with random condition. That should be something very familiar. Remember that we use this, so it's really crucial for doing inference. If the data doesn't come from a random sample, you can't draw conclusions about the larger population. Your estimate will be poor. So the second one, when sampling without replacement, the 10% condition ensures that our formula for the standard deviation is approximately correct. That's the same as always. And this next one is, we've done it before, but it's been a long time. So instead of RIL, we really have RIN. normal condition. So we're looking at the normal condition to ensure that it's appropriate to use a t-distribution to calculate a critical value for your t, or your t asterisk. So n is going to be our normal condition, and this is a little bit different, so we're going to talk about this one specifically. Okay, random, we know that. 10%, we know that. Now let's talk about this normal. Now before we talked about the central limit theorem, right? If things are greater than 30, we're good. But the whole point of a t-distribution was to be able to handle smaller sample sizes. So let's take a look at some of these conditions. It says the normal or large sample is if the population has a normal distribution, we're good. Or if the sample size is large, we're good. Right? So this is always the case. If it's normal, we're always fine. We don't have to check the central limit theorem. Now we're saying, okay, if it's greater than 30, that's great. We're going to check this according to the central limit theorem. We can say that it's good enough. But now there's this extra one here. If the population distribution has an unknown shape and the sample size is less than 30, we can use a graph of the sample data to assess the normality of the population. And then if we see a strong skew or an outliers, we cannot use t-procedures. So this new step is, hey, you know what? If it's less than 30 and we don't know if it's normal, look at the graph. Does this look normal? If it looks normal and has no strong skew or outliers, then we can use the t-score. So using t and the t-statistic wisely. An inference procedure is called robust, and this is a new stats term here for us, if the probability calculations involved in the procedure remain fairly accurate when a condition using the procedure is violated. Right, so an inference procedure is called robust if the probability calculations involved in the procedure remain fairly accurate when a condition for using the procedure is violated. In English, a confidence interval is robust against a non-normal distribution, meaning that a confidence interval is still pretty accurate even when the distribution isn't normal, right? So what we're saying is, look, when we're looking at a t-distribution, even if it's not a normal distribution, if it's skewed in some way, as long as it's not strongly skewed, we're okay. And what they mean by accurate is approximately 95% of the confidence intervals would capture the true mean if we're trying to do a confidence interval of 95%. A confidence interval is not robust when there are outliers or it is strongly skewed, meaning that the confidence interval is not accurate anymore. So if I have a huge skew or crazy outliers, this is not going to work. So what the t-procedure is trying to say is, look, if I'm skewed a little bit, that's okay. We can still use it. Strong skew, not okay. So here it is kind of summing up. So conditions for using t-procedures. If the sample size is less than 30, use t-procedures if the data appear close to normal. So let's define that. We're going to say close to normal is I'm looking at roughly symmetrical, I'm seeing one main peak, and I'm not seeing a lot of outliers. Do not use the t. So do not use any sort of t-score or a critical value for a t if there's a large skew or any outliers. And I put a little asterisk here because this is super important. If you have a sample size that's less than 30, they're going to want you to draw the distribution. Common ways to do this are a histogram or a dot plot or a modified box plot. I tend to do whatever is easiest based on the data that's given to me. Okay, but you have to draw a picture showing that you checked it. Even if you check it on your calculator and you're like, yep, it looks normal, they want you to draw a rough sketch of what this would look like so that they know that you've thought about it. And then if the sample size is at least 30, I can use t-procedures even if it's really skewed data. So that doesn't, so that's kind of cool. So let's try a sample problem for this. So this is conditions for estimating mu. Determine if the normal or large sample condition is met in each of the following settings. So to estimate the average GPA of students at your school, you randomly select 50 students. Here's a histogram of their GPAs. So 50, that's a key thing right there. Like I can look at this histogram and yeah, it looks roughly normal, no strong skew, but I don't even care about that. I've got 50. That's greater than 30, so I'm good. Let's check and see how we did. Yep, the sample size is large. 50 is greater than 30, so it does not matter what the histogram looks like. We're good. Let's try another. Okay, so how much force does it take to pull wood apart? The stem plot shows the force in pounds required to pull a piece of Doug fir apart for each of the 20 randomly selected pieces. So I can see this and I can see, well, 20, that's less than 30. So I really need to look at this distribution. Now, a stem plot, I kind of have to turn it on its side and think, all right, well, this is going to go this way and then kind of go that way for the stem and leaf plot. So if I'm looking at that, I would say, wow, that is strongly skewed to the left. I don't think I can pretend that that's normal under any circumstances. So I'm going to have to say, no, I can't use T procedures on this one. Let's see how we did. No, the stem plot is strongly skewed to the left with possible low outliers, and N is less than 30. Nice work. Last one for today. Suppose you want to estimate the mean SAT math score at a large high school. Here's a box plot of the SAT math scores for a random sample of 20 students at the school. So 20 is less than 30. I need to look at this distribution. Now it's kind of hard to look at it from a box plot, but I'm assuming that it's unimodal. So that's a little bit of an assumption there. But remember that this is 25% of the data, 25%, 25%, and 25%. So I have my peak somewhere here. I'm going down like this. And there is a skew, but well, that was actually not a great picture there, huh? There is a skew, but it's not necessarily a strong skew over here. So I would say it's like a slight skew to the right as opposed to what we saw on the other slide. So I'm going to say that, yeah, we can use this. Even though there's a skew, it's just a slight skew, so we're okay. All right, yes. Even though N is 20, which is less than 30, the box plot is only moderately skewed to the right, and there are no outliers. Again, I'm assuming that they would have drawn a mod box plot and shown me outliers with little stars so that I would know that there were outliers, not actually having to calculate them at this point. Okay, that's it. You can go ahead and go onto your OneNote and start your homework for your homework that's due tomorrow. Thanks.